All right, hello and welcome to Modeling with Quadratic Functions. So this is the point where I say it's learning how to swim in a way. So I can teach you the drills, I can teach you the formulas, I can walk you through kind of formulaic math. But to synthesize what you've learned and then apply it is kind of like learning how to swim. I can't really swim for you. I can help you and guide you, but ultimately you need to be able to use your resources and knowledge about quadratics to model and answer problems. So I tell my students that this is like kind of pushing you into the middle end of the pool where you're not going to sink, but we have to figure out what you need or you do in order to swim, and it just takes some patience and time. All right, so some of the things that you can do to help yourself out while you're working through these problems: to draw a picture and then interpret the shape of the picture, write down the information that you know, write down what you're trying to accomplish. Given what you know and what you need to accomplish, then write down information that you need to know, and then use what you have, your resources, your knowledge, the data that's given, your formulas to get what you need. And that's how you solve these problems. So I'm going to go through 3 examples. You're going to have 3 different problems to solve. All right, so here's the first one. So a bridge has 2 towers that rise 307 feet above the roadway. So you can see this tower is going to rise 307 feet above the roadway, and they're connected by suspension cables. So the top of the suspension cable is 307 feet. Should probably lower this to, whoopsie. I should probably lower this to 307 feet, if I can do it. So that's the idea. The height of the tower is 307 feet. Top is a cable. And I'll mess with the left-hand side later. And the cable can be modeled by the function y is equal to 1 over 7,000 times x minus 1,400 squared plus 27, where x and y are measured in feet. Assume the left side tower is the y-axis. What is the distance d between the towers? So here's my distance, so we're drawing the picture, right? And what is m, the maximum or vertical height from the roadway? So essentially we're looking for that vertex, the location of the vertex, so we can find out what the height of the cable is above the roadway. Okay, so this is how we're going to do it. I am going to find out what the axis of symmetry is, and then using the axis of symmetry value, which is really for t, I'm going to go ahead and find what the distance is by filling it out. So let me go through the values with you. So you can see pretty quickly that we have this equation in vertex form. So my vertex is going to be 1,427. So I'm going to mark off 1,400 here and then 27. And because this cable here is symmetric, I know that the distance here I can find by doubling the length from the origin to the vertex. So 2 times 1,400 leaves me at 2,800. So this point here is 2,800. So the distance d between the towers is going to be 2,800. And then the minimum vertical distance for the roadway is going to be 27 feet. And we got that based on the vertex. The vertex, 1,427. And we know because of symmetry, we just multiply 1,400 times 2 to get 2,800. These two distances from 0.0 to this d here at 1,400 and 1,400 to this point here where the suspension cable connects with the other tower is 2 times 1,400 or 2,800. All right, so that brings us to first classwork problem 2.4.1. So this is a similar problem. Each cable joining the 2 500-foot towers in the Golden Gate Bridge can be modeled by the function here, where x and y are measures in feet. What is the height h above the road of the cable at its lowest point, and how far apart d are the towers? So you can take a moment here to write this down, and I'm going to move on to our next problem. Okay, so number 2, the path of a place-kicked football thrown at an angle, let's just say, path of a place-kicked football, we're going to say kicked here at an angle of 45 degrees from the origin can be modeled by this equation, where x is the horizontal distance in yards and y is the height of the football in yards. How far is the football kicked? What is the football's maximum height? What is a reasonable domain and range in the context of the problem? All right, so let's take a look. This is we have intercept form here, and we can write this as negative 0.26 times x minus 0 if we wanted to write it out that way. So it would look something like negative 0.026 times x minus 0 times x minus 46, where we can identify the intercept form, the two x-intercepts at 0 here, and then 46 here. And that means that halfway between the two, since I started at the origin, is going to be 23. So then I'm going to use that value of 23 to solve for my value of y, which is really the height, as a function of x. All right, so I'm going to rewrite this then in standard form. I can also do that. And then I'm going to use minus b over 2a to find out this is 23. And then I'm going to use this 23 value to find the height. My height all right, so I have this value here of 23. This is the value for x. And then I want to use that value to substitute that back in to this equation to find the height at 23, wherever x is 23. And so I substitute, I have my equation here, and I'm going to substitute 23 back into the equation. So negative 0.026 times 23 times 23 minus 46 is equal to 13.754, so that's my maximum height. So then a reasonable domain and range would be 0 to 46, because I don't really have any negative values, even though there would be in this particular parabola for y. So I'm just going to consider all the positive values here. So my reasonable domain would be from 0 to 46, and a reasonable range is going to be from 0 to 13.754. All right, so that brings us to our next classwork problem, 2.4.2. So same thing, path of a place-kicked football kicked at an angle of 45 degrees can be modeled by the following function below. And so you're going to figure out how far the football is kicked, what's the maximum height, and what's a reasonable domain and range in the context of the problem. All right, so you can copy this down, and I'm going to move on to our next set of problems. Okay, last one, this should be 3. The path of a rocket can be modeled by following y is equal to negative 16 t squared plus v times t, that's velocity, plus h sub 0, where the initial height of the rocket is h sub 0. If the velocity is 64 feet per second and the initial height is 10, find A, the maximum height, the time at which the rocket reaches its maximum height, and the distance traveled by the rocket. Okay, here we go. So I'm going to draw this picture here. Here's my height, find t. I'm going to rewrite my equation with the velocity 64 feet per second. And then I'm going to find out what the vertex is, because the vertex is going to give me the y value for the maximum. So it's rewritten in standard form. I'm going to find the value for the axis of symmetry. It's actually t is equal to 2. And then I'm going to substitute that value back into the original equation to find out what the maximum height is. So remember, I found that axis of symmetry to find the vertex because the parabola faces down. I know the maximum height is going to be at the vertex for y. So then I evaluate where t is equal to 2, and I end up with 74 feet. So 74 feet is the maximum. Now the next thing I need to do is I need to find out where this function crosses the x-axis, and it's going to be in two locations. One location is going to be behind where it was kicked. This is going to be an extraneous solution. And then finally, I'm going to have some value where it crosses the x-axis, where y is equal to 0. So I want to use a quadratic formula to solve this function for y is equal to 0. And I end up with two equations. Here's my work. Are two values, 4.15 and negative 2.15. And again, this value is extraneous, so 4.15 is going to be the time that the ball is in the air. Now, this brings us to the second graph, because this is really a time graph. We could also create a distance graph over time. And so what we want to do, but that graph is going to be more of a linear function because the speed of the ball is 64 feet per second. It's constant. So we take the amount of time that it's been traveling, we multiply it by the velocity, and you get 265.6 feet is the distance that it has traveled. All right, so this brings us to the end, and I am going to leave you with a classwork problem. So you can see time here is 2 seconds for the maximum height of 74, and time for the total distance 4.154, which we multiply by 64 feet per second. So this brings us to our second classwork. Sorry, this brings us to our third classwork problem, third and final. So you're going to go ahead and evaluate, you're going to evaluate this problem here. So same thing, but the velocity now is 40 feet per second, the initial height is 20, find the maximum height and the distance traveled by the rocket. All right, so that brings us to the end of this session. Thanks for joining us, or joining me. Remember, there are going to be lots of other problems that don't necessarily follow these rules, but you have to, and you can, and you will use whatever tools that you've learned and the general process that I've given to you in order to solve these modeling problems. Thanks for joining. Come back and get the answers. And remember to upload your classwork to the appropriate location once you've finished.